Good morning, gentlemen. Today is Monday, June the 8th, and for today, we are going to talk about the last lesson involved in modern physics. All right. Now, this lesson itself deals with the current understanding of the structure of an atom. All right. We call this the standard model of particle physics. Now, in chemistry last year, you obviously spent a lot of time talking about the structures of protons and electrons and neutrons, because those are the major subatomic particles. But it turns out that neutrons and protons and electrons are composed of even smaller particles. And that's what this lesson is really all about. Now, I honestly don't know if you talked about the standard model of particle physics with Mr. Leonard at all. So this may be new and surprising to you. But what you need to understand to start here is that the fundamental particles of nature, the standard the standard model of particle physics, is reliant on an understanding of the fundamental forces of nature. Now, there are, I hope that you now understand, four major fundamental forces in nature. All right, I've listed them here in this table by their relative strength. All right, the strong nuclear force is the strongest of the four, and we give it a relative strength of 1. The electromagnetic force, which is Coulomb's law, is about 100 times less or weaker than the strong nuclear force. The weak nuclear force is far less than that, 10 to the negative 13th relative strength. And notice that the gravitational force is exceptionally weak compared to the strong nuclear force. Now, the second column, or third column actually in this table, is the range that these forces exert themselves over. And so the strong nuclear force is very, very small, or has a very small range of 10 to the negative 15th meters. And the weak nuclear force is less than 10 to the negative 18th meters. So that's 1,000 times less than the strong nuclear force, weaker than the strong nuclear force. Notice that the electromagnetic and gravitational forces don't have really a range, but rather are proportional to the inverse of their distances squared. All right, and you know that both from Newton's law of universal gravitation and Coulomb's law of the electrostatic force. What you may not realize is that there are particles that are referred to as force carriers, and they are listed in the fourth column here. A gluon is the force carrier particle for a strong nuclear force. The photon is the force carrier for an electromagnetic force, and we talked about photons previously in this unit. The weak nuclear forces are governed by particles called bosons, all right, both the W bosons and the Z bosons. More on that a little bit later. And these are the first particles that actually have mass, all right, 80.6 giga electron volts, which is obviously very small, and a charge of either positive or negative 1 fundamental charge, all right, 1.60 times 10 to the negative 19th coulombs. Now, finally, a graviton is the force carrier molecule, or particle rather, for the gravitational force, and it's got, again, no mass and no charge. So what does this all mean? Well, the subatomic particles actually are found on your reference table. This is on the third page, and there's two things that you need to be aware of. The first is the chart that says classification of matter, and you'll notice that matter is divided into two different particles, hadrons and leptons. Hadrons are further subdivided into two particles called baryons and mesons. And baryons are composed of three what we call quarks, and mesons are composed of a quark and an anti-quark together. All right. Now, what in the name of God does all of that mean? Well, on the right side of that page is the particles of the standard model. And you can see here there are two kinds, quarks and leptons. Now, the quarks are listed here. We have an up, down, top, bottom, strange, and charm quark. And then the leptons are divided into electrons, muons, the tau lepton, an electron neutrino, a muon neutrino, and a tau neutrino. So electrons and electron neutrinos, muons and muon neutrinos, tau and tau neutrinos. All right, now let's go back to the first picture there, whoops, over here, all right, and talk about the hadrons. Now, a hadron is defined as a particle that interacts through the strong nuclear, electromagnetic, weak nuclear, and gravitational forces, okay? And so all four of the forces are listed here, right? So these hadrons are particles that we are actually quite familiar with. The first type is what we call a baryon. And there are two kinds of baryons. They are protons and neutrons. Now, we used to call them, we still call them nucleons in terms of their chemical properties, but in terms of their physical properties, we call them baryons. And each baryon is composed of three quarks. Now, a proton is composed of two up quarks and a down quark. And if you look at the table of quarks there, you'll notice that the two up quarks each have a charge of positive 2/3 of an electron. So the total positive charge on a proton is positive 2/3, but then they're also composed of a down quark, which is negative 1/3. So positive 4/3 plus one negative third, or negative 1/3, gives you a charge of 1, just 1, okay? Now a neutron is composed of two down quarks, which gives you a total negative charge of negative 2/3 of an electron, or a standard charge, and one up quark, which is positive 2/3. So negative 2/3 and positive 2/3 gives you a charge of 0. All right, that's why a neutron is neutral. So the baryons are each composed of three quarks, which allows them to have either a positive 1 charge or a 0 charge. Now, the second type of hadron is a meson, all right, and they, again, are shown here, all right, and they are composed of one quark and one anti-quark, okay, and we'll talk about them. Well, we probably won't talk about them anymore, but that's what they are and where they are. Now, moving along. In terms of leptons, now the most famous of the leptons that you know of is an electron. And notice, though, that a lepton is defined as a particle that interacts through the electromagnetic, weak nuclear, and gravitational forces. Now, notice which one is not represented there. Which of the four forces is not there? The strong nuclear force is not represented here. Now, leptons are the electrons, the positrons, which is essentially just a positively charged electron, and neutrinos, all right? And those are shown at the bottom of the particles of the standard molecule, the particles of the standard model chart that you see at the bottom of here. So there's the leptons, all right? Now, you can see that there are electrons, muons, and tau leptons, and each of those has an anti-particle. So An electron, the opposite of an electron is a positron. All right. The opposite of a muon is a positively charged muon, and the opposite of a tau is a negatively charged tau. All right. Now, in addition, there are also neutral leptons called neutrinos, and there's an electron neutrino, a muon neutrino, and a tau neutrino. All right. So for each of these particles, there are also antiparticles. So just keep that in mind. Now, we're not going to get into any more detail, honestly, with these subatomic particles. But I just wanted you to be aware of them. Someday, if you do take AP Physics or a physics course in college, you will no doubt talk about these in greater detail. But for our purposes here, and given that the end of the semester is coming very, very rapidly, we're going to leave it at that. All right, so matter is broken up into hadrons, which are essentially the protons and neutrons with some other particles in there, and the leptons, which are essentially the electrons and the particles similar to them. Okay. Now, in terms of the matter that we generally think of when we're talking about these kinds of things, everyday matter, the desk that you are working at, the chair that you are sitting on, the food that you eat, and so on, they are generally composed of a down quark, an up quark, and an electron. All right, or some combination of downs and ups, and electrons. So they're made of baryons and leptons. All right. And you can figure out, again, what makes a proton, what makes a neutron, what makes an electron. Now, cosmic rays actually have a somewhat different makeup. All right, they are composed of charm quarks, strange quarks, and muons. All right, these are other different particles that you find, and again, they are all listed here, so you can look at them and kind of put together what what they might compose. But cosmic rays are rays that are put forth by stars and other cosmic entities. And then finally, it's believed theoretically that during the Big Bang, other particles were produced, including what we call the top quark, the bottom quark, and tau particles. All right, so that covers, if you look at your chart on that page, that covers all of the particles of the Standard Model. All right, everyday matter are the downs and up quarks, as well as the electrons in terms of the everyday matter. The charm quark and the strange quark, as well as muons for cosmic rays. And then finally, the top quark and bottom quark, along with the tau leptons for the Big Bang. All right, and so all 12 of the particles are listed in terms of this, including the neutrinos. So that is a brief introduction to the idea of subatomic particles beyond protons, neutrons, and electrons. And that, my friends, is the end of our discussion on modern physics. Tomorrow, we will begin a brief discussion on Einstein's theory of relativity. So, happy Monday, and I will see you soon.